Good morning, good afternoon, good night again, and thanks for joining today. My name is Fabrizio Lamberti. You probably know me already. I'm the Vice President of Technical Activities for CTSoc, and today I'm here to open this new webinar of the Technical Talks of CTSoc series. So, probably the technical activities area is one of the new areas of CTSoc, besides publications, conferences, standards, educational activities, history. And the idea is to support the other areas of CTSoc through a number of entities. And a key role is played by the technical committees. The technical committees have been launched at the end of 2020, beginning of 2021, and so far we have 15 technical committees which are recognized to be the engine of our society. As you see, they cover the broad areas and all the areas of our society so far, but of course new technical committees can be established. As you can see, the technical activities is organized as an area, organized with the 15 technical committees which report to the technical committees board. And the members of the technical committees board are myself, CTSoc President, Professor Wenchun Kao, VP Conferences, Professor Nobuo Funabiki, VP Publication, Professor Fabrice Labo, who is also the President-elect, the new President for 2025 and 2026, and VP Industry and Standard Activities, Rahed Abdullah, with the officers, chairs, vice chairs, and secretaries of the 15 technical committees. In the technical activities area, there is also the Future Directions Committee, which is in charge of identifying new areas in which the CTSoc can be involved. Each technical committees, I assume that many of you are members of the technical committees. Each technical committee has its mission and vision, has its officers, has its members. And these are the current officers of the technical committees, which are serving for the 2023 and 2024 term. And the new officers will have to be elected this year for the next 2 years. Today, we'll have two technical committees represented, the IoT, Internet of Everywhere, and Edge Computing, and the CPE, which is Consumer Power and Energy. In case you know someone who is interested in joining our technical committees, please direct them onto the main website of CTSoc, and on the website of CTSoc, on the right, under technical activities areas, there is a link for accessing this page, the technical activities membership application form, and submitting on your application, submitting their application. The new application will be evaluated, and if selected, the new applicants will join the community of today, approximately 900 members who decided to join or were invited to join our technical committees that, as you know, as you can see, are covering, the size can be slightly different, but they are all well represent the areas of interest for CTSoc. The role of the technical committees is support CTSoc in all the areas, conferences, publications, standard education, and history. They are supposed to create additional CTSoc interest for other possible technologies and support the development of new cross-cutting initiatives in other areas, also in collaborations with other society, council, and organizing units. For instance, just to give you an idea of what the technical committees are doing in the areas of conferences, the technical committees are responsible for reviewing and approving the call for papers of conferences, supporting the conferences by contributing papers and reviewing, providing publicity, collect nominations for volunteers willing to serve in the technical positions of conferences, but also providing conference tracks and session chairs, etc., etc. And similar objectives are pursued in all the areas, like the publications. For instance, we periodically seek for associate editors. We periodically seek for volunteers willing to organize special sessions in journals, etc. We are also organizing a number of activities in collaboration with other societies, with other units, with other organizations. So one example, one of the most recent example is the IEEE Gaming, Entertainment and Media Conference, which is currently accepting submission, and the various roles in the technical committees have been covered through the technical committees. I want to give you another example. Well, the call for paper is open, so if you are interested in this topic, please do consider submitting. And another initiative that I want to present today is the digital reality technical community. So it is not the technical committee, it's something broader. There is an initiative that is named IEEE Digital Reality, which is about the Internet of Things. It's about digital twins, it's about digital transformation, it's about the metaverse. And this initiative has been funded under the Future Directions Committee, and after the period as an initiative is now transitioning into a technical community. So it's something broader than a technical committee. It's not a CTSoc level. CTSoc is leading this transition, but it is sponsored, financially sponsored by other society councils or organizing units like the Reliability Society, the Electronic Packaging Society, the Engineering and Medicine and Biology Society, the Council on Radio Frequency Identification, IEEE Standard Association, and other discussions are in progress. So in case you and the other members of the technical committees are interested in participating, that will you receive call for volunteering. Now, coming to the technical talks, and I want to steal more time to this to today webinar. As you know, we are building on the success of initiatives that are growing up in the technical committees, and we decided to create a unique time for members of the technical committees and other to join and listen to presentation talks prepared by members of technical committees. And today, it's the time of the IoT and the CPE technical committee. So I would like to thank the chairs and officers of the IoT technical committee, Liang Bichen, Nagaran Perumal, and Aaron C., and of the CPE Technical Committee, Lucio Ciabattoni, Vijadar Subudi, and Rajiv Ranyan, for having secured the participation of Professor Christos Antonopoulos and Professor Badwinder Rai. They represent two technical committees, so you see they will give two topics that are connected by the use of AI. So I would first of all introduce Professor Christos Antonopoulos from University of Peloponnese, Greece, and the title of his talk would be From Embedded to AI-Powered Cyber-Physical System and Beyond. So Christos, the floor is yours.
Okay, thank you. Thank you so much. So let me share. Okay, I guess you're seeing the right screen, right?
We are seeing it with notes, so we see both so probably you need to share another screen or change the way. Yes, that's perfect.
Okay. Thank you very much. So thank you very much. For the introduction, I will try to keep it short and of course have questions or communication afterwards. So the idea here is to talk how in our laboratory we started from the embedded systems and we are trying to utilize artificial intelligence to go to what is called cyber-physical systems and even beyond. As the moderator indicated, my name is Christos Antonopoulos and I'm assistant professor at the University of Peloponnese. Okay, a few words about us. I'm also Deputy Director of the Embedded System Design Application Laboratory at the Electrical and Computer Engineering Department of University of Peloponnese. And these are the main contributors to this work, my colleagues from postdoc researchers to fellow professors. Now, instead of an introduction, we are going to ask some questions, like basic questions like why AI and why now, and then try to understand why new applications require embedded systems more and more, particularly when we want to exploit and leverage artificial intelligence, and then present two specific examples that we have developed in our laboratory, which I hope are going to be of interest to you and provide, let's say, some food for thought and questions, of course. Now, the simple question is why AI? It is simple because basically the answer is AI has indeed offered the tools to solve problems that we could not solve previously. And some of these problems may be easy to solve, but some other problems are quite hard to solve. Okay, but we believe that most importantly, we need to ask why now? What has changed and AI approaches and algorithms are so popular, they are so hot. One thing is to follow the market. For the last few years, let's say from 2020 approximately, we have entered what it is called the AI big data era, where we have trillions of units that have processing powers. They have adequate processing power that they can actually be exploited in order to implement and be used, actually used in AI based scenarios. This in turn has also provided input to the market, and we have more and more indications like AI-related growth will boost global GDP by $16 trillion by 2030. This is 5-6 years from now, so it's quite close. So this is one thing, the market and the fact that we have so many devices that can actually be used is driving this, this research area. Additionally, we all know that CPU and GPU farms in the cloud are very popular. They are very easy to find, process, and collect data. We are all using them. Okay. So theoretically, someone can say that we have all the tools that we need. In the cloud, we can say that we have unlimited resources. That is only partially true, because apart from the resources, we need to consider also the requirements and the growth of requirements. And what has been clear after more than 1 decade is that particularly for AI-based applications and application scenarios, the requirement growth is much higher than the resources growth. More than 10 years, even the Moore law has been validated, since the requirements growth is increasing by 3.4 months per year, instead of the expected 18 months that the Moore law has indicated, and we have all followed for many decades. So this means that we need to follow another approach. And this is where edge computing and embedded system and cyber-physical system comes into play. They are enforcing, or they are strengthening the approach that cloud is not suitable for modern applications, or let's say not suitable for all modern applications. Particularly when the applications are extremely tight concerning the latency and response. As we are when we are dealing with human life and emergency situations, when we need bandwidth, and bandwidth cost is not free and the capacity is not always there. Then you have security. When you are using cloud, basically you are transferring and processing data in potentially open and public network, which is inherently risky in relation to using, for example, embedded systems. Then power consumption is also a critical factor. Using the cloud, of course, and cloud computing is extremely energy hungry. We all know that if we have developed or we are working in any kind of data center or high performance computing center, this is a critical factor. And as we all know, there is this data obesity factor, meaning that it is not expected that data are going to be reduced. Quite the contrary, they are going to continue to increase. So transferring everything to the cloud is no longer the obvious solution. Some applications are better exploit the edge computing paradigm. So this covers, let's say, the starting point of our work. And now I'm going to present two examples how we are trying to exploit this approach. The first one has to do with localization, and particularly since we are talking about Internet of Things, RSSI-based localization. Received signal strength indicator is the basic raw measurement that we are using in order to estimate the distance between two IoT sensors and then try to figure out the exact location of a node or of a sensor. This has been increasingly required in many application scenarios, research-based or even commercial, where we have where we need to provide assistance services, monitoring, security, and others in areas of living. We are targeting mainly indoor scenarios. That's why I'm saying living areas. This is particularly important when we are dealing with aging people or people with specific disabilities. The idea here is to use IoT devices and AI machine learning technologies in order to provide accurate, low-cost indoor positioning system that can be used by any kind of wireless technologies. This is the workflow that we are following. First of all, we focus on how to aggregate data, RSSI collection. It can be done for any wireless communication, but since we are targeting indoor position, indoor scenarios, we are mainly focusing on Bluetooth low energy embedded systems. Then we have the data enrichment step, where we have the first, let's say, contribution of our team, where we are able to minimize quite significantly the communication overhead at the edge layer. Basically, we try to transmit only the absolutely necessary information to the cloud, and everything else happens on the cloud. Then you have the RSSI processing and filtering. This is a quite notorious problem, because correlating RSSI measurements to distance, it is indeed very hard, since RSSI is a very volatile and unpredictably changing measurement. So we need to have algorithms, and we have developed our own custom RSSI filtering approach. Then, on top of that, we are using machine learning techniques in order to be more accurate regarding the estimation of the distance. Therefore, apart from having our own custom RSSI rater, we are also applying machine learning approaches. And then we have the localization estimation, where we are using trilateration in order to estimate the exact coordinates of the sensor. This is the high-level architecture. We have two layers: the edge layer that contains all the devices, BLE beacons, gateways, where you can use Raspberry, you can use basically any ARM-based platform, and then you have the cloud layer with message broking, data stream pipelines, and the data storage. Now, the RSSI collection. The RSSI collection is done every 2 seconds, and we are able to collect 20 RSSI samples. Then the tracking object is connected to the local gateway, and all this information is transferred to the cloud. The communication flow is comprised by 2 steps. First of all, from the object to the gateway, and then from the gateway to the cloud. A critical development that we have done is to use MQTT communication protocol end-to-end. MQTT is very well known and, of course, widely utilized for backend communications. But being able to use it from the sensors, from the sensor layer up to the cloud layer, it enables us to have a truly seamless and effective communication and data transfer approach. And then we have the data payload that it is actually transmitted by the sensors to the cloud. Now, a critical part, as we said, is the data enrichment, which happens at the strings aggregation. Here we collect all the strings from the data, and we have the enriched beacons and obstacle information. What is important here to highlight is that although for the localization we are using this in the middle JSON format, we are actually wirelessly transmitting only the information that we see on the left-hand side of the slide. This is to indicate how streamlined and how reduced is the actual information that we send wirelessly. This has drastic beneficial effect both on the bandwidth requirement, on the power consumption, and on the data delay performance of our system. And then we go to the processing, part. Here we have two parts of processing. First of all, the RSSI signal analysis, and then the location process. The first one. For the first one, we, as I said, we have developed our own RSSI rater, our own RSSI filtering approach. Basically, what we are doing is that we are separating the RSSI samples to chunks that are more than 3 samples, and we are using standard deviation in order to evaluate if each particular chunk is good, has good measurements, reliable measurements that we can use for distance estimation or not. And then if the standard deviation is above a specific threshold that we can configure, then we are keeping the measurement. Otherwise, we are rejecting the measurements. So we are trying basically to keep all the reliable measurements and reject all the non-reliable measurements. But this is not enough. This is not enough. And this is where machine learning comes. So we are not relying just on the good measurements, but we are using these good measurements, these RSSI good measurements, to feed a machine learning model. In this case, we are using the Orange platform, which is a very user-friendly and very effective, efficient platform. We can use automatically and evaluate a very high number of different machine learning algorithms. In our case, the best measurements were extracted by the multi-layered perceptron with backpropagation. For the specific examples, we have used the typical 80-20 train set split ratio, which after heuristic approach in order to find the best configuration, the best machine learning parameters, like the number of hidden layers, the activation function, the weight optimization solver, and so on, we are able to have very accurate distance estimation for a range between 0.5 meter to 4 meters, which is typically indoor scenario for our cases. And actually, we have tested it in more than 4 different indoor scenarios. As we can see, the accuracy is in most cases more than 70%, and in only one case it drops slightly below 70%. So our system is indeed quite reliable. And then we are using a nonlinear least square optimizer in order to estimate the position. Basically, this is a very well-known algorithm, Levenberg-Marquardt. It is easily implementable, but you can also find it implemented in 4 various platforms, and it relies on trilateration. And then we are also transforming these coordinates when we want to present it in another coordinate system like Canvas. which is more popular when you want to present something. So this is our approach to use IoT devices, low cost, low complexity IoT device, and combine it with AI in order to increase the localization accuracy. The second example I will briefly present is related to the health domain, and particularly regarding the knee rehabilitation. In this case, what we want to do is accurately measure and monitor a very simple movement, the range of our knee, of our leg. Why? Because orthopedic doctors that are actually driving this work have correlated this range with quite significant everyday life activities, without which we can indeed suffer. And what has been observed is that even a slight loss of this range of motion can actually lead to pathological phenomena, obvious pathological phenomena. And this is this happens very frequently if we just imagine that that there are 4 million arthroscopic knee procedures conducted in every year. So it is very important to have a system that is able to detect, monitor, and inform doctors for extended periods of time regarding the post-operative knee range of motion restoration process. But to do that, the big idea here is to actually have the machine learning model, the trained machine learning model, executed on the embedded system, not on the cloud, because this device must be taken by the patient to his or her house for a 1 week to 3 months period. So the platform that we have developed, as you can see here, starts from from step 1, where all the information is collected. Then we have developed our own backend platform, and the machine learning model is trained using the edge impulse at the cloud. But here is the novel idea. The trained model, we can now download it to the embedded system, to a very low cost, low complexity embedded system. So this system can be directly used by the patient at any place, his or her house. This is the main goal, the final goal. Okay. To do that, we rely on Arduino Nano 33BLE sensor platform. We are trying to monitor angles ranging from 20 degrees to 120 degrees, and we have considered 3 setups. A lab-based setup with a goniometer, just a goniometer, then the embedded system on the leg of the patient. This is the most realistic, let's say, scenario. And another scenario where the patient actually wears a specialized orthopedic tool, which basically bounds his or her knee and provides much more controllable scenarios. As I said, for this case, we use the edge impulse. This is another very interesting, easy to use and efficient platform that enables us through a very nice user interface to create the blocks for our system. A critical part has to do with the data acquisition. When you don't have data, you need to create data. And this is a step that took us a lot of time. To create our own data set, we didn't have a data set, so we created our data set, and we had to manually annotate all data. Edge Impulse gives us a very nice tool to do that and avoid mistakes, because any mistake in this case is going to basically ruin your machine learning model. Another question was, what are the raw measurements that we are going to use? In our case, we use the accelerometer values because this is the most typical value in any IoT platform. And although the dominant axis was 1, because we have a very simple movement, we considered all 3 different accelerometer axes, because what we found out is that even in simple and predetermined movements, there are micro movements in the other 2 directions. So our model was significantly enhanced when we consider all three axes instead of only the dominant one. So we ended up with a neural network with 80 to 20 train set split ratio. We considered features both at the time domain and the frequency domain, which ended up with a data set of 33 features, 11 per axis. Final results, very good accuracy in all cases. When considering the goniometer, this is the, let's say, the lab-based evaluation, we have more than 88% accuracy. And what was even more impressive is that even in small deviations, for example, between 45 and 60 degrees, 15 degrees deviation is very small, still the accuracy is very good and can be used in practical scenarios. In the more realistic scenarios, goniometer on the knee, of course, you have a slight degrees of the overall accuracy, but still 78 plus degree accuracy is good enough to conduct real-life experiments. And of course, when you have the specialized orthopedic tool, the knee brace that bounds the knee, then you have 100% accuracy in all cases. But as I said, the idea here is not just to train the model, but also to download the model on the embedded system. And this is what we did, hoping to reduce the bandwidth requirements, the detection latency, and increase the number of predictions in specific time periods. Once again, we use the edge impulse, which gives you the opportunity to extract the trained model for this particular platform and download it. Of course, you need to do some programming regarding the wireless communication, event detection, and so on. But this is something that, that we did. And what we ended up with is a very accurate system. The system accuracy is exactly the same as the one that you are using, that we had when we were using the cloud version. So the classification accuracy is always at the same level. Very, very small deviations not worth mentioning. But what it is worth mentioning is that we have more than 99% bandwidth reduction and thus also drastic reduction concerning the energy consumption. 39 to 40% reduction of the delay, the event detection delay, and 70% increase regarding the event prediction. So basically, what we were able to provide to the doctors are a system that can be used for more than 1 month, for sure, at home, a drastic reduction regarding the bandwidth and the power consumption, lower latency, and much better privacy and safety conditions for sensitive private data. So I will not take any more time. Thank you very much for this kind invitation and for your attention. And please, if you have any questions, either now or even offline, don't hesitate to use my email. Thank you very much.
Thank you very much, Christos, for this very interesting talk. I have personally some questions, probably also the audience, but for the sake of time, maybe it's better to first leave the floor to Balwinder for the next talk, and then if time remains at the end, I would be happy to invite the audience and also myself to ask questions, if it is okay with you. So I would share again my screen just for 1 second in order to introduce also Professor Balwinder Rai. In this case, he represents the Technical Committee on Consumer Power and Energy. He is from the National Institute of Technology, Jalandhar, India, and his talk will be low-power semiconductor memories for AI applications. Thanks again for accepting the invitation to and volunteering in this case to give a talk. The floor is yours.
Thank you, sir. Thank you very much for a nice introduction. So it's my pleasure to be here. So let me share my screen first, and then we will talk about it. Yes, I hope my screen is visible to each and everyone connected here.
It's visible. I don't know if you want to go full screen or you remain like this, as you prefer.
Yes, let me make it full screen. Yeah.
No, because probably you are sharing your the application and not the screen, so we don't see full screen, but still.
Is it fine, or I share my complete screen?
Yes, because so far we see the application, so it's not full screen.
Okay, let me stop sharing and share my screen again. Please confirm, is it fine now?
No, it's still we still see the PowerPoint application with the slides on the left and the image on the center. So you can go like this if you like.
Is
Yeah,
it
perfect. That's fine. That's great. Please,
okay? Should I continue?
please.
Okay. So, thank you very much for giving me invitation to be here and share my brief work about low power semiconductor memories for AI application. So, let me briefly introduce. I did my PhD from India, Indian Institute of Technology, Roorkee, and for my postdoctorate work, I was in Italy itself from in 2010 to 2011 in University of Rome, Tor Vergata. I worked with Professor Ernesto Limti in Rome. So that was a wonderful time to stay there, and it's really nice to be here again at this platform for discussion. So as I mentioned, the memory design, semiconductor memory design for AI. Here, I would like to mention the hardware requirement for AI is parallelly we have to grow along with the software development. So if we see the in any sector, the memories are very important. Major companies like NVIDIA, graphics, Qualcomm, all are working how we can make the smart memories for AI applications. Memories are not new. It's people are using from last 4 5 decades. But the thing new that we require from AI perspective point is we have to make the memories non-volatile. So static memories specifically they are volatile once the power is off, the memories whole data is off, and that is not basically acceptable by the AI application for robotics. For that we require SMRAM to be a non-volatile type. So if we see a system on chip, nowadays the key technology behind each and every products for robotics and AI, here each and every module or segment is going to be on a single chip. For that, I would be more have focus on this memory part only. So how we can make this memory smart in terms of interaction with the processor so that the less time delays there and high speed along with the power optimization techniques can be applied. So let me come to the semiconductor memories. So if we talk about the hierarchy of the semiconductor memory in computer system, we have the different levels from hard drive to main memory to cache memory. So cache memory basically focus on the SRAM. Here the target to interlink this SRAM with the AI technology. So if we classify the memories, memories are used from RAM, ROM, volatile, non-volatile, SRAM, non-volatile RAM, buried RAM, FRAM. So from a ROM perspective, one type program. So my concern is here, I am more interested in this part only, non-volatile RAM. So to make this non-volatile or conventional MOSFETs, they are not suitable. Now we have to think about how we can make the device structure in such a way so that the device itself consume as less as power possible, so that once we integrate this device in our memories so that the memories also consume less power. So for this, if we make a comparison in the various memories, this although the data is older enough, but my concern is here to justify the performance of the RAM with the other memories like DRAM, EPRAM, flash, FRAM. So here how we can make the speed and power trade-off as minimum. Whenever we try to improve the power in the memory, speed degrades, and when we try to improve the speed, power degrades, this trade-off we have to be minimized with the alternative memory structures. So this is the very basic memory organization where we require the huge memory cells in the various nodes. So I skip some of the basic slides. Let me come on the various techniques how we can minimize the power requirement in the memories. So if we have this source biasing, forward bias, reverse bias, dynamic type, floating body, negative word. So these are some of the techniques by which we can minimize the power requirement in the static memory cell. So we cannot achieve each and every targeted point here, but the thing is, if you can see here, if we reduce the leakage current specifically for the sub-threshold leakage current, gate leakage current, band-to-band tunneling. So if we try to minimize this, then our delay also increase a bit. So to minimize this trade-off, we have to go for the overhead like low transition overhead stability. So with these, we can implement these techniques in SRAM, and we try to came up with the optimized memory size so that the power requirement can be minimized. So for the SRAM stability analysis, we have carried out here, and we find out the static noise margin for the SRAM. This SRAM we designed with the FinFET structure, but nowadays this is FinFET and CMOS. They are also only for the conventional memories. We can say use these are not suitable for the AI applications. If we have to migrate to the AI, we have to be switch to the spintronics based memory or spin based memory. But still in the stability of the SRAM is improved with the improved with the FinFET structure. So here this rectangle part shows the we have to find out how much this diagonal length of diagonal is there in this rectangle. Larger the length of diagonal is there means more stability of the SRAM cell is there. Now the thing is how we can achieve this larger length of the diameter. We have to make the inverter characteristics of the individual cross-coupled inverter in such a way they move near to their ideal characteristics. So we also design 60 and 80 SRAM and find out the analysis that there is 30% improvement is there in the speed with the 80. But at the same time, there is some area enhancement is also there. Let us discuss how we can make the memories low power. So to see, first we have to identify where the power is consuming, where the power is dissipated so that we can minimize those power requirement. So the measure of the power goes into the leakage power and threshold due to the threshold voltage reduction of the individual devices. So for that, we have to be design the new devices with the variable threshold voltage, dual threshold voltage, so that the in the off state threshold voltage can be enhanced, in the on state the minimum threshold voltage can be there, so that the net its I on by I off ratio of the device can be improved. So this is one of the technique known as Venn organization in the SRAM, where the number of the word line and row line and width lines are quite large. If we have a large memory, we can divide the memory in small segments, and here we divided the whole memory in the 4 banks, and suppose we have to store or retrieve the data from one bank, we can activate only that particular segment of the memory, and we can deactivate other part so that the power consumption cannot be there. At the same time, power dissipation also can be minimized in the way the switching capacitance is basically the target is to minimize the switching capacitance. So the same way we can, there is another technique known as the divided word line architecture, where because in the architecture you can see we have a large number of this word line and bit line. We can divide them in small segment, and being a random access memory, we can access any part of the memory. And if the size of memories are quite large, then this hierarchical word line decoding can also be used. Here the number of this division in the different techniques can be further increased. End goal of this memory hierarchical is the how we can minimize the power requirement. There is another technique known as the pulse generator, where basically we have to incorporate some delay in the circuit, so that this part of further the number of inverters required in a chain can be minimized or increased or decreased depending upon the actual delay requirement in the sense amplifier to analyze the target bit 0 or 1. So this is about the conventional memories, static memories. Let us discuss briefly the advanced semiconductor memories. Like I mentioned, CMOS or FinFET, they are volatile and conventional technology. Now, if we have to integrate this memory with the AI application, we have to go for the resistive memories. So this SRAM, DRAM, flash memory, they are the conventional technology with the CMOS. No, resistive memories with the memristor. Memristor is one of the device that have the resistance with the memory, resistor. Okay, so that can be used to design the memory. So as I mentioned, for the AI application, we require the non-volatile memories. So memristor have the properties that once the power is off, still the memory, device can store its value. Then the PCM and STMRAM magnetic junctions, they can also be used as the interface from the technology point of view to have the memories for the AI application. So let's discuss brief about the spin devices and memory for AI. So spintronics is the new nanotechnology, where the movement of the representation is not because of the charge, but it is the rotation of the charge. So in the conventional devices like MOSFET, the charge can be moved from source to drain, but here the rotation of the charge up or down, clockwise or anti-clockwise, they represent the value stored in the memory, either 0 or 1. So spintronics is basically the two words combined together, spin plus electronics. Spin is the rotation of the charge carriers, and how we can take this positive rotation or negative rotation, we represent the memory 0 and 1. So this is basically the spintronics structure from its rotation point of view. It's clockwise or anti-clockwise. Accordingly, we represent the two possible bits 0 and 1. So here, if we talk about the power density versus technology node, as we reduce the technology node, the power requirement is also keep on increasing from here, and because of the individual leakage current in the conventional devices, and this is as per the Moore's law also. But this need of spintronics mitigate this challenge that we are facing in the conventional devices. So if we give the pros and cons of the spintronics technology, that is the non-volatile, and that is very much compatible with the AI requirement. So why we are migrating from microelectronics to nanoelectronics and this spintronics? Because it's consumed less power, it is faster, it have low cost, as well as no data loss is there if there is a sudden power off is there. How we can migrate to this new technology? We have to, these are some of the features they have the inherent, like spin value, GMR, MTJ, multi-junction devices, then organic spintronics, hybrid spintronics. So these are the features we have the good point from its spintronics point of view. So MRAM, magnetoresistive memories, is also a feature that is very good from AI point of view. From non-volatility, high speed performance is there, low cost is there. So this is basically the comparison of different memory from the structural point of view, as well as their how they are having the different benefit, merits and demerit in terms of the non-volatility, its low cost, its endurance, how long they can hold the data. Because the conventional memory, specifically DRAM, have the limitation, the data cannot be retained for long, because once the charge degrade from the capacitor, their data erase automatically. Here, that challenges also overcome with these spintronics and magnetic memories. This is the structure of the MRAM, how they store the values. Basically, here we have the two layers, magnetic free layer and the this magnetic printed layer, pin layer, and in between there is tunneling junction is there. And this is basically hybrid with our conventional transistors, so that their operation can take place. So let me come to the MTJ design for AI application. This is the MTJ structure that we have designed in the LT Spice, and this is the open source tool. You can design your device here. You can came up with a symbol, and this symbol further can be used for the circuit application. Here also we have two layers. You can see free layer and fixed layer. Free layer is where we can make it either the clockwise or anti-clockwise, and the fixed layer is having the charge in the same direction. So we analyzed and compared, we designed and got up with the TMR ratio. We compared this result with some reference data reported from the literature, and we have found the same trend for our proposed MTJ structure as well in the reported. We also evaluated the present work. This is one of my PhD scholar working on this for the STT RAM, and he evaluated and compared with the reported data, and we are getting the quite interesting results for the same. We analyze the resistive properties, the resistance, its STT RAM component, TMR ratio, threshold voltage, thermal analysis. That is very important from the AI application point of view, because our target is to have a memory with low power as well as high speed. So thermal analysis can also be carried out with the technology scaling. Then we came up with the MTJ symbol.
Professor, right, we have 3 minutes remaining, so
sure. I'm let me bind up in
no,
another
probably we
minutes.
were late,
I
but if
can
you can
understand time constraint. So let me skip the result part. These are the results that we obtained, and let me just came up with the final comparison. This is the final comparison that we made with the reference SRAM cell with the STT MRAM. So this STT MRAM we have discussed. This is quite interesting from the AI application point of view, and we are getting the good results for the same. So let me conclude what we did here. We started with the simple AI application. The spintronics is the key, where we can have the migrate from the CMOS technology to spintronics for the AI application, so that we have the non-volatile memory. So the main performance of this memory further can be enhanced with the hybrid and comparison with the CMOS. So these are some of the references. So I thank you one and all who are here and giving me the opportunity to discuss the work with you. So now house is open for the questions. Questions, please, if there is any.
Thank you, Bawinder and Christos. I think that unfortunately we ran out of time, so I would encourage those who have questions for our speakers to send them directly either to them, or they share their contacts or to me, and I will forward them to the speakers. I want to, well, I think that this talk shared that two different, the activities of the members of two very different technical committees, one working on IoT, on healthcare related sensors and wireless related sensors on the one side, and memories on the other side are well, very different, but they are benefiting from the development of AI and this related technology. So I think that these pitches were of interest for the attendees and for those who will look at these recordings after the meeting. So I thank you once again. I thanks again the TCs that you represent, and I invite you to join in one of the next event of this series. Thanks again.
Thank you very much.
Thank you very much. Good night. Thank you. Bye-bye.
Bye-bye.
Well.